lot of work, and they've been doing a fantastic job. So I'm going to be talking about the cyclic sieving phenomenon, and this is meant to be an introductory talk. So please, if there's anything that's not clear, stop me. I'm happy to answer questions because I'm not going to be using any very high-powered mathematics. This is meant to be understandable to the general audience. And if you like what you see here and want to have a record of it, you can just surf over to my webpage and you'll find a copy of the slides. So that address is all you need to write down from this talk. So let me give you an outline of what I'm going to say. I guess I have to point this way. Come on. Wrong button. If there's a binary choice, I'm bound to make the wrong one. Okay, I was pressing the backward button, and it can't go backward from the first slide. Okay, so we'll start off, like I said, there's an introduction, so I'm not assuming you know anything about cyclic sieving, so I'll have to define what cyclic sieving is for you, and then I'm going to introduce an example which is going to follow us for the whole talk, which is going to basically, I don't know about you, but me personally, I learn best by doing examples. So this example is really, hopefully, where you're going to learn most about what cyclic sieving is and how it works. And most cyclic sieving proofs that are in the literature are of one of two flavors. There's proof by substitution of roots of unity, and so the second section will give you an example of that kind of a proof. And the other kind of proof uses techniques from representation theory, and in order to give that proof, I'm again not assuming that people know anything about representation, so I'll give you just enough representation theory to be able to understand the second proof, and that should finish off the talk. So let's, as I said, start with the very beginning. So in order to have cyclic sieving, you need three ingredients. The first of these, or actually the first two of these ingredients, are a set S and a finite cyclic group G acting on that set. Okay? And then we'll need some notation in order to express what we're talking about. So if I've got a group element, little g and big G, then S to the G is, as usual, just the set of fixed points of that element. So the set of all little t that get fixed by the element, little g. And we'll also need a notation for the order of the element. So this is the order of the element as in the big group G, right? The smallest power of that element that gives you the identity. So we'll let O of G be that. And we'll be using in the background all the time Lagrange's theorem, which says, of course, that if D is the order of a group element, and here D, whenever you see D now, you should think order of a group element, because that's what it's going to be used for. D always divides the number of elements in the group. I'll be using this pound sign for cardinality. Okay? So, and usually the order of the group is going to be n, so you're going to be seeing D divides n, and that's all that that's referring to when you see that. Okay. And then another thing we're going to need is we're going to be dealing a lot with roots of unity. So omega sub d is going to be a primitive d-th root of unity, which you might as well take to be e to the 2 pi I over d, if you like. And what you should be thinking of is that omega sub d corresponds to the group element G because they have the same order, right? The order of G in the group big G is the same as the order of omega d in the group of all roots of unity, right? And so somehow G and omega sub d correspond. And in fact, if you liked, you could set up some sort of isomorphism between the two groups involved. And then the final element that we need is some polynomial in Q, f of Q. And now I can tell you what the cyclic sieving phenomenon is. So this following definition was originated in a paper by Vic Reiner, Dennis Stanton, and Dennis White. By the way, I just got email from Dennis Stanton yesterday, and he sends his greetings to all of his friends here. So if you're a friend of Dennis Stanton, you should consider yourself greeted. And so this is the idea behind cyclic sieving. So this triple consisting of the set, the group acting on the set, and this polynomial exhibits the cyclic sieving phenomenon if, for every element of the group, if I want to calculate the number of things that are fixed by that element, right, one way I can calculate that is to plug a corresponding root of unity into my polynomial f. Now this is a little bit bizarre when you first see it, because if I plug a root of unity into a polynomial, I expect to get out some sort of complex number which is going to have non-zero, right, I component. But this is saying not only when I plug in these complex numbers do I get non-negative integers, they actually count something. So this is, and so you might think, is this ever going to happen? I mean, this seems like a very hard condition to meet. Actually, it seems to happen all over the place. Before we come to the example to illustrate this, let me just make a couple of notes. First of all, this definition was inspired by work of John Stembridge in part, where he studied the special case where the group has order 2. So now you're just looking at something where you've got the square is equal to 1, and therefore John called it the q equal -1 phenomenon, right? Because -1 is the unique primitive square root of unity. And as I said, interest in this phenomenon is starting to grow. So here's a partial list of people that have worked on this, some of whom are in the audience, some of whom are even giving this talk. And if I left out anybody in the audience who's done work on this, my apologies. This list is probably not exhaustive. Okay, as I said, everything is easier with an example. So this is the example that's going to haunt us for the rest of the talk, so we might as well get nice and used to it. So brackets n, as usual, is going to be the numbers 1 through n. And then the set that I'm going to choose for my cyclic sieving here is, is what I call brackets n double choose k. So this means you're going to take all k element multi-subsets of brackets n, right? So I'm going to take all ways of choosing k elements from 1 through n with repetition allowed. That's why we've got the double brackets here. So if I've got such a multi-set, multi-sets, of course, they're not considered as ordered, so we're going to always put them in a canonical order, which is going to be weakly increasing. So right here are the k elements that I've chosen. I put them in weakly increasing order, my canonical order, and they're, of course, numbers between 1 through n, because that's what I have in my ground set. Okay, so that is the set S that we're going to be dealing with. So we're going to get really specific here. Let's look at case n equals 3 and k equal to 2. So then that would mean we would be looking at all subsets, or not subsets, multi-subsets of 1 through 3, which have 2 elements. So we have the ones where we have a pair of elements like 1, 1, 2, 2, and 3, 3, and the other ones where we have 2 distinct elements. Okay. So, very important fact to note that will come up later in various forms. One of the first things that you prove in an elementary combinatorics course is that the number of ways to choose k things from n things with repetition is this binomial coefficient. Okay, so this is something to keep in the back of your mind. So that's the set that we're interested in. What's the group? The group is going to be the simplest possible group you could think of. Take the n cycle that sends 1 to 2, 2 to 3, and n back to 1, and take the group generated by that. Okay? How does that act on my set S? Well, in kind of the obvious, okay, so here back going to the example, here's the group generated by the cycle 1 goes to 2, goes to 3, goes back to 1, right? We have it square, 1, 3, 2, and then we have the identity element. And what's the action? Well, it's kind of the action you'd expect. Acting on a multiset, an element just acts on each element individually. Right? So G of M is just G of each of the individual I sub j. And again, let's see what that looks like in the example. So let me compute the action of the generator 1, 2, 3. Well, on 1, 1, right, 1, 2, 3 sends 1 to 2. So on 1, 1, it's going to send it to 2, 2. Similarly, 2, 2 is going to be sent to 3, 3, and 3, 3 to 1, 1. A little bit more interesting example is here, right? 1 gets sent to 2, so this 1 will become a 2. 3 gets sent to 1, so this 3 will become a 1. That gives me 2, 1. But remember, these are unordered. So I'm really going to always think of this as the element 1, 2, as the unordered version of this. Okay, so that is our crucial example, and that's what everything else in this talk is going to be based on. Are there any questions about what's going on in this example? Good. I like that. But if there were questions, questions, I would be happy with that too. Okay, so we've given you the set, we've given you the group, and there's one missing piece of information. What is this polynomial? So let me tell you what the polynomial is going to be. So for this we need some standard, what are called Q analogues. So the Q analog of n, brackets n sub q, is just this nice geometric series, 1 plus q squared up to q to the n minus 1. And it's called a Q analog of n because if I plug in q equal to 1, then I'm summing up 1 n times, and that gives me n back. Now, there is, of course, a lot of brackets now floating around because I'm also using brackets n for the numbers 1 through n. But when I'm using it in this sense, I'll always put a little subscript q. So that'll tip you off whether I'm talking about the set or the polynomial. Now, there correspondingly are also factorials in the land of q. And the factorial is kind of what you'd expect. You just, to get brackets n factorial, you just take brackets 1 times brackets 2 up through brackets n. And then finally, you have analogues of the binomial coefficients, where brackets n choose k is brackets n factorial over brackets k factorial. Right? You just write brackets around everything. Now, one thing that's not obvious from this is that this is actually a polynomial in Q. Just like it's not obvious if I define the ordinary binomial coefficients in terms of factorials that you're getting an integer and not a rational number. But it is. These things do divide.
How difficult to prove?
Very easy to prove in any number of ways, and if there's time at the end of the talk, I would be more than happy to show you. Probably the most straightforward way to prove it is these things satisfy a recurrence relation, very much like the recurrence relation, and then once you have the recurrence, you just induct. Other questions before we go? Like I say, I'm not assuming you've seen any of this Q analog stuff before, so feel free to ask. Okay, so here is pretty much the first theorem, somewhat watered down. They actually prove a stronger result than this, but again, for the sake of making things simple and understandable, the first time you see this, I'm going to do this absolute possible simplest case of this theorem in the paper of Stanton, Reiner, and White. So the cyclic sieving phenomenon is exhibited by k multi-subsets of 1 through n, the group generated by the n cycle, and the Q, remember, n plus k minus 1 choose k was the number of things in my set S. We'll just put brackets around that, make that into a polynomial in exactly this way, and you get cyclic sieving. Okay, so why is this true? Well, as I said, I'm going to give you 2 general proofs, but before we do that, let's see why it's true in the particular example that we were looking at with n equal to 3 and k equal to 2. Okay? So what is f of q in this case? Well, I've got to plug 3 and 2 into this polynomial here, right? So I get 3 plus 2 minus 1, choose 2, which is 4, choose 2. And now if you just multiply, right, you can multiply these things out and do division and some cancellation, you will get the following polynomial. Skip some simple algebra. Straightforward algebra. So now we have to verify the cyclic sieving equation for each of my 3 elements of the group. Right? So I've got to verify that the number of fixed points is what I get by plugging in the corresponding root of unity for each of the elements of my group, where my group is the group generated by the cycle 1 goes to 2 goes to 3 back to 1. Well, let me just do that in a case-by-case fashion. Suppose I start with the identity, the simplest possible thing. Well, what's the corresponding root of unity? Obviously 1, right? That's the only thing that has order 0 in the set of roots of unity. And what happens when I plug that into my polynomial? Well, clearly I get 6, right? I'm just summing the coefficients. And that's the number of things in my set S. Because remember, let's go back here and look and see. We had the set S up a little while ago. Right? There it is. And you can just count. 1, 2, 3, 4, 5, 6. Or you could use the formula that was on this slide before. So that gives us the number of elements in S. Oopsie. So that gives me the number of things in S. But of course, that's also the number of things fixed by the identity, because everything's fixed by the identity. All of S is fixed by the identity, so it works, right? I plugged in 1, I got the number of fixed points for the identity. What about 1, 2, 3? Or we could use a 1, 3, 2 as well, right? They both have order 3, so it's not going to matter. And so let's take the appropriate cube root of unity, e to the 2 pi I over 3, and see what happens when I plug that into the def. Well, then, of course, you just get that where q has been replaced by omega everywhere. And now think about it. This is a cube root of unity, right? So omega cubed is equal to 1, so we can add those two together and get 2. Omega to the 4th is equal to omega, so you can add those two together to get 2, and you get this. But now remember, e to the 2 pi I over 3, one of the principal properties of nth roots of unity, if you sum 1 plus omega squared up to omega to the n minus 1, you get 0. So this is 0, and I claim that is the number of fixed points. Why? Well, again, we computed back on the previous slide, right, the action. Right? Here is the full action of 1, 2, 3 at the bottom two rows. And you can see there is nary a fixed point anywhere. All of these things get sent to different elements. So it works in this example, and obviously, therefore, it works in general, so thank you for listening to the talk. No. We are going to give you rigorous proofs that this works in general, but does everybody see why it works in this particular special case? Questions about this? Okay, so onward and upward. So as I said, we now have two standard ways of proving these results. One of them is by substitution of roots of unity, just like we've been doing here. So let's give you that proof first. That's the most elementary of the two types. So here's how you could prove this by substitution. Well, obviously, we're going to need some results about what happens when we substitute roots of unity into these Q analogues of binomial coefficients, and in particular, what happens if we just substitute roots of unity into just brackets n sub q. So here's the necessary result we need. Suppose an m and n are congruent mod d, and take, as usual, omega to be your primitive dth root of unity. What happens to the ratio of mq over nq as q approaches omega? The reason I'm taking a limit rather than just plugging right in is it's possible that the top and bottom are 0. So you may have to take a limit to get something not 0. Well, it's very nice. One of two things happens. If n is divisible by d, which of course means that m is also divisible by d because they're congruent, then you just get the ratio of the corresponding integers. So that's really pretty. And in all other cases, you get 1. So it's very simple, and it's also extremely simple to prove. Look, think about it. Suppose m and n, they're congruent. Suppose r is their residue, right? So some number between 0 and d minus 1. And now what happens if I try and plug omega into m? Right? So it's a geometric series. So what am I going to get? I'm going to get 1 plus omega squared. And once I get to omega to the d minus 1, I can forget about those terms because they sum to 0. Right? This is a dth root of unity. Well, what about the next d terms? They also sum to 0. And the next d, and the next d, and the next d. So what's going to happen is you're going to get a bunch of things that sum to 0 at the beginning, and at the very end, you'll get these last few terms, which will only be a partial sum out to whatever the residue is. So, right? So basically we're saying we can ignore terms in groups of d here except up through these last r. But does this matter that I'm doing this with m? I could do this with n as well, right? M and n are congruent. So I can have exactly the same procedure. I may have a different number of groups of d that are 0, but that's of course not going to change the sum. So this, in fact, is equal. You get the same thing if you do this with brackets n. Well, now we're done with the else case because, right, suppose d doesn't divide n. If d doesn't divide n, then this last piece here will not be 0. So neither of these are 0, so I just divide that onto the other side, and I should hopefully get 1 in that case. What happens if d does divide n? Okay, so we've done the else case. I hope you all agree. What happens if d divides n? Well, remember, m and n are congruent, so d also divides m. So write n as some multiple of d, say L times d, and m as some other multiple of d. And now it's not hard to see that if I take the ratio, again, now thinking of these as polynomials in Q, we can factor out of both the top and the bottom 1 plus q up through q to the d minus 1. Right? Because think about it. If I multiply this by 1, I get the first d terms here. If I multiply this by q to the d, I get the next d terms here, etc., 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 etc. So if I cancel these guys out and plug in my omega, which is equivalent to taking the limit, what's going to happen? Well, this was the part that was making the top and the bottom 0, but they were canceled. What am I going to get? Remember, omega is a dth root of unity, so omega to the d is going to be, this is a test, 1, and omega to the 2d is going to be 1, and so we're going to get a sum of a bunch of 1s, and how many 1s are we going to have? K of them, right? Similarly, on the bottom, we'll have L. But remember, K and L are in the same ratio as M and N, just by a factor of D. So we're done. Okay? Everybody believe this, though? Good. So, now we're going to go on from there and see what happens if you now, what we really want is to plug these into these Q binomial coefficients. And here again, turns out to be very nice. So if d divides n, right, and omega is a primitive dth root, and I plug it into n plus k minus 1, choose k, right? That was the thing that we were interested in our cyclic sibling, the polynomial. If d divides k, I just get the corresponding binomial coefficient where I divide everything that's divisible by d. The minus 1 has to stay where it is. And otherwise, I get 0. Again, this is really easy to see, so let's go through the proof. Okay, so this is the heart of the proof right here. Remember that d divides n. And look at the, right after we do cancellation, look at the products that are left on the top and the bottom. On the top, we'll have n times n plus 1 up through n plus k minus 1. And on the bottom, we'll have k factorial. Think about what these things are when we plug in omega. Well, remember, we saw on the last slide, when we plug in omega, if the thing that we're bracketing is divisible by d, it zeroes out. And if it's not divisible by d, it's something with that last little term in the end. So when I plug in omega to this, that's going to zero out, right? Because d divides n. This next one will not 0, 0, not 0, not 0, not 0. So we're going to start with a 0. Then we're going to have d minus 1 things which are non-zero. And then it's going to repeat, right? We're going to get n plus d with omega plugged in. That's going to be 0. So it's periodic, right? A period d where we're starting with 0. What's going to happen on the bottom? Well, it's essentially the reverse, right? We start off with brackets 1, which is non-zero, brackets 2, which is non-zero, and we have to wait till we get to brackets d to get something which is 0. So as we go along in both sequences and compare how many zeros we've seen, we'll always be seeing at least as many zeros in this top sequence, because it starts with a 0 in the period, than we do in this guy, which ends with a 0 in the period. So we always have at least as many zeros as the top and the bottom. And when would we get equality? We can only get equality if, in fact, k is divisible by d, because when k is divisible by d, right, that'll be that last 0 in the period. So that's the crucial thing. So then think about it. What happens if d doesn't divide k? If d doesn't divide k, we have more zeros in the top than we have in the bottom. End of story, right? That's this case, the else case. Whoopsie. Right? The else case says that if d doesn't divide k, we get 0, and that's because we got more 0 terms in the top than we have in the bottom. What if d does divide k? Well, again, let's write out what we've got here. And I'm cheating a little bit. I'm subscripting everything with omega where I should really be taking limits. But I think you'll accept that cheat, I hope. And notice I've written things out a little bit. On the top, we've written things out in increasing order. In the bottom, I've written things out in a slightly different order. Right, here's 1 through k minus 1, and I put k at the beginning. Why did I do that? It's because I want to have the top and the bottom congruent mod d. Right? D divides both n and k. These are both 1 mod d. These are both 2 mod d. But what do we know about ratios? of things where they're congruent mod D. We just proved something about that, right? So if I go back to the previous slide, or let me not even bother, let me just remind you, right? If they're both divisible by D, you get the ratio of the corresponding integers, and if they're not both divisible by D, you just get 1. So you're going to get n over k here, and then d minus 1 ones. And then the next one you're going to get is n plus d over d, and then d minus 1 ones, et cetera, et cetera, et cetera. So how can I make this into a binomial coefficient, right? The bottom, these guys on the top and the bottom now are no longer consecutive integers, but you can fix that by dividing everything by d. Right? That's why I need to divide things by d, because if I divide things by d, now on the bottom I have k over d factorial, and on the top I have exactly what I need to have that binomial coefficient. Okay? So now we know what happens on the right-hand side of cyclic sieving, right? Right-hand side of cyclic sieving was what happens if I plug omega into my polynomial. We've just seen what happens there. So what happens now on the other side? Okay, so suppose I have one of these multisets, and I have an element of order G. What does the fixed number of fixed points look like? Well, I claim that if D divides K, the number of elements in my multiset, I get n plus k over d minus 1, choose k over d, and guess what it is if d is not divide k? 0, right? Because this is exactly, whoopsie, come on, cooperate, exactly what we had on the previous slide. Right? So this says the two sides are equal, because we physically computed them, and it turned out to be the same. So why is this true? Well, okay, so we need to take a group element of order D, and I'm going to take the n over dth power of the cycle. Now, of course, this is not the only group element of order D, but it's the simplest to deal with, and the other ones, once you see it, the proof for this, it's easy to figure out what modifications you need to take for the other elements of order D. So let's use this. Okay, so what does G look like? Well, G in its cycle decomposition then sends 1 to 1 plus n over d, and then to 1 plus 2n over d, et cetera, and then 2 to 2 plus n over d, and 2 plus n over 2n over d, et cetera. And I'm going to need names for the cycles. So let G1 be the first cycle, G2 be the second cycle. And I'm also going to use these guys not just for the cycles, but also for the set, the underlying set. And it'll be clear from context which I'm talking about. So G1, sometimes I'm going to use just for the set of numbers, 1 plus n over d, 1 plus 2n over d. So what does it mean to be fixed? I claim it means the following. An element is going to be fixed if and only if it can be written as a multi-set union of these cycles, G1, G2, so by multi-set union, this U plus, I mean you're counting things with multiplicity, right? So if I take 1, 1, 2, multi-set union 1, 2, 3, I have 3 total 1s, 2 total 2s, and a 3. Why is this the case? Well, one direction is easy to see. What if M can be written in this form? Well, think about it. What does a cycle do to the elements in the cycle? It just permutes them around. Right? It doesn't change them, doesn't send them anywhere else. It just permutes them among themselves. So each of those cycles is going to be fixed, right? Because the cycles of G just permute the elements in each cycle around. So if M can be written in this form, it is definitely a fixed point. And it doesn't take much to convince yourself with a little bit of time and thought that the reverse is true. Okay, so that's the crucial fact. And now things are simple, because think about it. Remember, how big are each of these cycles? Well, they're D cycles, right? Because this is an element of order D. And so in order to get the identity when I raise to the D power, we're going to have D elements in each cycle. Or you can just think, right, there's going to be n over D of the cycles, and we started with n original elements, so there's D elements in each cycle. So suppose D doesn't divide the size of the multiset we chose. Is it possible to write it in this form? Clearly not, right? We're taking union with multiplicities. So if GI1 has D things in it, and GI2 has D things in it, and they all have D things in it, their union is going to, has to be of size a multiple of D. So if the total number of things we're supposed to get is not a multiple of D, there's no way of doing this. And if there's no way of doing this, there's no fixed point, right? Because this was the characterization of what the fixed points look like. So that's why we get 0 in this case. Okay, what about the other case? Well, if we do have a fixed point, then it's going to be a union like this. How many cycles are we going to have in this union here? Well, remember, I need k total things in M. Each of these guys have D things. So if I need k total things and I've got D in each, I've got to take k over D of these cycles to put in this union. And the original G factored into n over D cycles, and we're allowing repetition, right, because these are multisets. How many ways are there of choosing k over D things from n over D things where you allow repetition? It's that formula we saw on the first slide, right? Right, so that's the notation for it. And it's just, right, sum the top and the bottoms, minus 1, choose the bottom. And that's the other. And we are now very much done. I hope you agree. Questions about this? Any questions? Okay, so if that got too technically involved, we're about to change viewpoints radically, so you can wake back up. Any questions? Okay, well, let me go on. So now I've got to give you, just, like I said, just enough representation theory to be able to prove this result in representation theory terms. So here's how we're going to think about things. So again, suppose we have a group acting on a set. Let's say the elements of the set are S1 through Sk. Then there's a corresponding action of G on a vector space created from this set, which I'm going to denote as CS, where C is the complex numbers. So what we do is we think of the elements of set as vectors, and when I do so, I'm going to write them in boldface. So whenever you see these boldface, I'm thinking that's going to be a vector. And I just take all formal linear combinations of these vectors with coefficients in the complexes. And that's easy to see that that's a vector space, right? You can add 2 of these things formally by doing it component-wise. You can scalar multiple one by just, again, doing everything component by component. So there's the vector space corresponding to the set S. Now, what happens with my group action in this case? Well, I claim that each element of my group now becomes a linear transformation, an invertible linear transformation on the space. Why? Think about it. What does G do on the set level? On the set level, G just permutes the elements of S. But when we move up to this vector space, what are the elements of S? They're a basis for this space, right? I'm defining the space to be all linear combinations of this. So they span and are linearly independent. So if I have a map on a basis, what can I do to get a linear map? Linearly extend. Right? Just take the linear extension of this map defined on the basis, and the fact that it permutes the basis, that it takes the basis to itself, means that the thing's going to be invertible, right? Because invertible maps, that's what invertible maps do for a living. They take bases to bases. Okay? So I'm going to denote that linear map by brackets G. Now you're going to say, oh my God, he's using brackets again. He was using brackets. But this should be a little bit easier to distinguish because in the other cases I was always doing brackets N where N was a number. Now we're using brackets G where G is a group element. So these can be hard to confuse. But if you have any questions, just ask. Okay. And we're also going to need a notation for what the matrix of this linear transform looks like in a given basis. And so I'm just going to subscript brackets G with the basis that I'm using. So what is the matrix of G in this canonical basis consisting of the elements in S? Well, it's just what you'd call the permutation matrix, right? Because in this canonical basis, right, G sends that basis to itself without multiplicities. It sends each basis element to some other basis element, and therefore if I compute this, it's just going to be a permutation matrix, a 0, 1 matrix with exactly 1, 1 in each row and column. Again, let's check to make sure that everything is understandable with an example. So take the group generated by 1, 2, 3, acting on the set consisting of 1, 2, 3, and there's my vector space, right? It's some scalar times the vector 1 plus some other scalar times the vector 2 plus some other scalar times the vector 3. So in this basis, this natural basis, what is going to be the corresponding linear map for the generator 1, 2, 3? Well, 1, 2, 3 sends the basis vector 1 to 2, it sends the basis vector 2 to the basis vector 3, and the basis vector 3 back to 1. And of course, the matrix that tells you how to do that is exactly this matrix, right? So the first column tells you that first element goes to second, the second column tells you second element goes to third, and the third column tells you that the third element goes back to the first element. Right? So far we don't seem to have gained a lot, but at least we have now a linear transformation where before we just had a permutation. Does everything look... This slide should be really crystal clear, so any questions about this? Okay. So we're going to have to be a little bit more general than these permutation spaces that we were just talking about. So a G module is just any vector space over C where G acts by invertible linear transformations. So now we just have a general place, and as long as we have an action of G, and the action is by invertible linear transformations, that's called a module for the action of G. And one of the most important things for us is going to be the character of this action. So the character of G on V is the function that takes each group element and gives you back the scalar, which is the trace of that linear transformation. Right? Now, notice this is a well-defined concept because it doesn't matter what basis, right? Well-known fact from linear algebra, you have a linear transformation, you take two different bases, the trace is invariant. Okay, so we can use any basis we like in taking this character. Let's see what happens when we take it in the basis consisting of S itself. Well, remember, what does this matrix look like? It's a 0, 1 matrix corresponding to the permutation. And so this trace is going to be a sum of zeros and ones. When are we going to get a 1 on the diagonal? Well, precisely when the group element fixes that vector. So this is going to be the number of fixed points, something we are very much interested in. So this is why we need characters, because if we look at the trace of an element with this action, we just get the number of fixed points. Now let's compute this character in another way. So this relates everything to one of sides of the cyclic sieving phenomenon. We now need to relate it to the other side involving the polynomial. And we'll need for that to have names for the coefficients of the polynomial. So here I've written the polynomial out as m sub I q to the I. So m sub 0 plus m sub 1 q, et cetera, et cetera, et cetera. And suppose there is a basis for CS such that every group element is diagonalized on this basis, which may seem like a lot to ask, but it's going to turn out that it's easy to do. And suppose further that the diagonal matrix you get has the following very special form. It has a bunch of ones on the diagonal, and the bunch is very specific. You've got M0 ones, where M0 is the constant term here. And then after that, you're going to have M1 omegas, and then M2 omega squareds, et cetera, et cetera. So suppose you could do this. I haven't justified you that you can't do this, but just suppose. Humor me. Suppose we could do this. Well, then what would be the character in this other basis? Well, how do we take the trace of a diagonal matrix? I don't think it's very difficult. Right? We're just going to sum up these elements with their multiplicities, the mi's. So by what we're assuming, we get the sum of m sub I omega to the I. And I think that's pretty clearly what you get when you plug omega into this polynomial. So this is f evaluated omega. But remember, the character is a trace. Trace is invariant. Doesn't matter what basis you use. So we've just computed it in 1 and 2 in 2 different ways, but they have to be equal. So we're done, right? If these two guys are equal, we have cyclic sieving, because that's, right, the right-hand sides are the two things we need for cyclic sieving. So this is why group representations can be used to prove cyclic sieving phenomena. Any questions about this? So this is the background that you'll need. And now we need to apply it to the specific example. Okay, so let's see how it works. Actually, there's one small little bit of extra information that we're going to need. So all of this has been working in CS, right, the permutation module for my underlying set S. We don't have to work there. We can work in any module which is module isomorphic to this. Module isomorphic just means they're isomorphic as vector spaces via some map phi, and phi preserves the G action. That is to say, if I were to act in V by some element of G and apply phi, I'd get the same thing as if I acted in, first of all in V and then went over by phi. You have a commutative diagram. And the reason we're going to need this is sometimes we can come up with a module which has more structure than CS does, and where we need the structure. And you'll see this in the example. Okay, so now let's back to our example, and let's see how we would prove it by representation theory. So here is that isomorphic module that we're going to need. So it's the space of k-fold symmetric tensors. So take your original vector space consisting of the vector space generated by the numbers 1 through n as vectors. Take its k-fold tensor product. Now, in a normal tensor product, U tensor V is not the same as V tensor U. So mod out by all the relations you need to make all the tensors commute. So what do the elements of this look like? Well, the elements, I'm going to use I sub 1 up through I sub k, that sequence, to denote the equivalence class of the tensor I1 tensor at I, the tensor IK, when we've done this modding out. So here's what sim2,3 looks like, right? So this is going to be all tensors of degree 2 using the vectors boldface 1, boldface 2, and boldface 3. So I can use boldface 1, boldface 1, boldface 2, boldface 2, or boldface 3, boldface 3. And then I can use 1, 2, and I don't need 2, 1, right? Because things commute. I can have 1, 3, and I have 2, 3. So that's what sim2,3 would look like. They're very simple objects. What's the group action going to be? Well, if I've got a tensor, or an equivalence class I1 through IK, as usual, I just let it act component-wise. I let G act on the first one, G act on the second one, G act on the next one. Have we seen an action like this before? Yes. This is exactly the action we were using on multisets, right? Let's go back and check. Right? Here. This is exactly the, whoopsie. Now what did I do? Too much technology. There we go. Right? This is exactly the same as the action that we were defining on multisets. So this is, so sim, these symmetric tensors, are exactly isomorphic to the permutation module, but it turns out that we'll need a property of sim that we don't have in the permutation module. So that's why we're using sim, even though we essentially have the same action. And now, because we've got two, right, we've now got two modules running around. We have the original module C brackets n, and then we have this new module sim kn. So we're going to need to distinguish, if I'm talking about a linear transformation, where I'm talking about it. Am I talking about it in the original vector space or in this new guy? So I'll just put primes if it's on the new guy. So for example, again to make sure, we've already computed what 1, 2, 3 looked like in the original module on 1, 2, and 3 as vectors, right? That was this, right? This is the matrix, this 3 by 3 matrix that we computed before. What about in this new sim gadget? Well, now my basis, so the primed version of this would now be in the basis for sim, which is 1, 1, 2, 2, 3, 3, 1, 2, 1, 3, 2, 3. Or I chose that basis to write down the matrix. And we've actually seen this matrix before also, although we didn't write it down in matrix form. Because remember, way back at the very beginning, we computed the action of 1, 2, 3 in my multisets. And what did it do? It sent 1, 1 to 2, 2, 2, 2 to 3, 3, 3, 3 to 1, 1. So we have a one little 3 cycle there, and then another little 3 cycle on 1, 2, 2, 3, and 1, 3. And that's just reflected in the matrix, right? This little block up here is that first 1, 3 cycle on the first 3 elements, and this little block down here is the other 3 cycle on these 3 elements. Okay, so, and again, consistent notation, chi and chi prime will be the traces in these two different modules. And now let's again make this diagonalization assumption and see where it leads us. So suppose I have a basis for the original module diagonalizing the original basis, the original linear transformation for G. Suppose the eigenvectors are x1 through xn. What's going to happen then when we bump this up to sim? So here's this, right, I said the reason we're using sim is because it has a crucial property which isn't in the permutation module, and this is the crucial property that we need. It turns out that if I have any basis for my original vector space, I can get an induced basis B prime for sim merely by taking k tuples of the basis elements from the original basis with repetition. Okay, so this is a well-known fact about sim. So if I want to compute what G does in the sim, I can compute it on this basis and see what happens. Well, think about it. So what happens when I apply G to a basis element? Well, by definition, I apply G to each of the individual guys. But remember, these individual guys are all eigenvectors, right? So G of Bi sub 1 is just going to multiply Bi sub 1 by the scalar x sub I sub 1. And similarly for B sub I sub 2, etc. So we're just, each of these G's is just going to give us one more scalar, and then of course is a tensor product, so we can factor all the scalars out in the front. And lo and behold, we have an eigenvector in the new action on sim, where the eigenvalue is just the product of the corresponding x's for these B's, right? So these eigenvectors from the original basis lift to eigenvectors in sim. So then if these guys are all eigenvectors, what is the matrix going to look like? Well, it's just going to be a diagonal matrix with these eigenvalues on the diagonal. So for example, suppose we're back to the case when n is 3, and we've got some basis which diagonalizes G. So the basis is ABC, and the eigenvectors corresponding are x1, x2, x3. What's going to happen if I now look at the version in the sim? Well, okay, so I'm going to have now basis vectors AA, BB, CC, AB, AC, and BC. What's going to happen on AA? Well, this tells us that the original thing multiplies A by x1, so it's going to multiply AA by x1 squared. And similarly, B gets sent to x2b, so that's going to multiply BB by x2 squared, etc. So we're going to get all the squares and all the ways of multiplying things. And those people in the know what adding those elements gives you. Right? So when I sum these guys up and finally take the trace, I get the sum of all possible monomials I can get by taking k of the x1 through xn. And that is known as a complete homogeneous symmetric function, h sub k. So here we would get, right? So h2 of x1 through x3 would be the sum of all monomials of degree 2 that you can get using the variables x1, x2, and x3. So you get the squares, and then you get the products of two distinct ones. Okay, so we are pretty much set. We just need one small lemma, which relates these complete homogeneous symmetric functions that we just popped up to my original polynomials that we were dealing with. So this is saying if for the variables x1 through xn, I substitute powers of q. This is called a principal specialization. It turns out that you magically get this q binomial coefficient. And it's, again, like was asked at the very beginning of the talk, this is not hard to prove by induction, but I don't have time. So let me just finish things off then. So I keep saying, if you could diagonalize, and you keep probably thinking, well, what if you can't diagonalize? Let me show you now that you can diagonalize. And this is really simple. Think about it. Look at the linear map corresponding to the generator in the original space. What's its characteristic polynomial going to be? Well, the nth power of this is the identity, right? So its characteristic polynomial is going to be x to the n minus 1. What are the roots of that polynomial? Well, 1 omega sub n, right? Primitive nth root of unity, e to 2 pi over n, if you like, etc., squares. But these eigenvalues are all distinct. What do you know about a linear operator, all of whose eigenvalues are distinct? It's diagonalizable, right? Because we can find an eigenvector for each of the eigenvalues, and they cannot be linearly independent because they correspond to different eigenvalues. So this thing is indeed diagonalizable, and there are the eigenvalues. But of course, I didn't want just that. I wanted to be able to diagonalize every group element. But of course, that's easy to do, right? Because every other group element is a power of this. So the diagonal, use the same basis and just, right? You'll get the matrix just by multiplying these diagonal matrices together. And when I multiply diagonal matrices together, they stay diagonal, right? So if I want what corresponds to the generator squared, I just square that matrix and cube that matrix, etc. So everything is nicely diagonalizable. And if you think about it a little bit, you'll see that the diagonal form of these guys has exactly the form that we got for the generator, except that rather than the nth roots of unity, primitive nth roots of unity, you're using primitive dth roots of unity, where d is, as usual, the order of this. And now we really are done. We've got all of the elements. Let's put them together. Okay. Remember, from the previous slide, we said that if we want to compute the character in sim, I take the homogeneous symmetric function in the eigenvalues for G. And the eigenvalues for G are this 1 omega up through omega n minus 1. Right? That's what we just had on the previous slide. But think about it. Do we know anything about what happens if we plug in powers into a homogeneous symmetric function? Yes, we have the lemma. The lemma tells you that if I take this principal specialization, I just get the corresponding q binomial coefficient evaluated at whatever thing you're using for the powers. So in this particular, the thing that we're using for the powers is omega. So now we have computed the trace in one way, in this diagonalizing basis. But remember, why did we pick sim to begin with? We picked sim to begin with because it was isomorphic to the permutation module. And remember, we showed that for any permutation module, if you use the natural basis, you get a 0, 1 matrix, and the sum of the diagonal entries is the number of fixed points. So because of the fact that these two are isomorphic, chi prime is also the number of fixed points. And again, if you've computed a linear transformation's trace in two different ways, you get the same thing. That's the end of the story. Thank you so much.